Hello, in this video we're going to take a look at a few basic notions of signals. So what is a signal? A signal is defined as a physical quantity that varies as a function of time, space, or any other independent variable. The most important thing though is that the signal should convey some information. So if we take a look at a couple of examples, in electrical engineering we often think of currents and voltages in an electrical circuit. Well, in this case, the current or the voltage represents an amplitude that varies as a function of time. So in this case, time is our independent variable. And it conveys information because it tells you the current or the voltage that might be appearing across a particular circuit element or at a particular node. You might also have radio communication signals, video signals, or data signals. These are all signals that are characterized by an amplitude that varies as a function of time. In mechanical engineering, you might have different types of waves, a pressure wave, a sound wave, or even a vibration. So these waves have amplitudes that also vary as a function of time. You might also have signals that are characterized by, for instance, an acceleration that you're tracking as a function of time, or the velocity that you're tracking as a function of time. In biomedical engineering, in addition to regular temporal type signals, you might also find images. You might be looking at an X-ray image, you might be taking a look at an ultrasound image. In this case, the image is characterized by an amplitude that's varying not as a function of time, but perhaps as a function of space. You might finally also have a financial signal. In this case, you might be tracking the value of a stock or the value of a mutual fund as a function of time. It's often easiest to represent a signal using the concept of a function. So a signal could be represented as x of t. In this particular case, t will represent your independent variable, and it takes on a value within the set D called the domain. X represents the range, or the dependent variable, and takes on a value within the set R called the range. The independent variable, again, can represent time, space, or any other physical quantity. In terms of classifying signals, these are usually grouped according to characteristics or attributes of the signal relative to the independent or the dependent variable. So for instance, let's take time as our independent variable. In this case, we can classify signals as being continuous time or discrete time. A continuous time signal is one where the independent variable t takes on any continuum value within the real number set. So the domain is any real number. Or the domain could be an interval within the real number set. On the other hand, if we look at a discrete time signal, the independent variable t is only going to be defined at discrete instances of time. So a discrete time signal is often obtained from a continuous time signal using the process of sampling. But what's important here is that if we look at the domain of the discrete time signal, these are integer values only. So let's turn our attention now to the range of the signal, or the amplitude. If we look at the amplitude, we can divide signals or classify signals into being continuous amplitude and discrete amplitude. A continuous amplitude signal is one where x, or the range, will take on a continuum values within the real number set or the complex number set. So if we have a complex valued signal, for instance. On the other hand, if we look at a discrete amplitude signal, the range, or x, the values of x, will only take on a discrete value within the real number set or the complex number set. So you'll often run into discrete amplitude signals when you do the process of quantization. Another classification of signals is whether they are periodic or aperiodic. So signal x is said to be periodic if you find some positive constant t naught, which is called the period, such that this relationship holds for all time t. The smallest value of t naught, or that satisfies this condition, is called the fundamental period. So in this example over here, in this function that's illustrated over here, you can see that this signal is going to repeat every capital T naught. So that's the fundamental period. If a signal is periodic, it will also be periodic not only in its fundamental period, but with integer multiples of the fundamental period. So this signal will also repeat every 2 T naught, every 3 T naught, every 4 T naught, and so on. If a signal is not periodic, then it is said to be aperiodic. So let's take a look at a couple of examples. Here we have x of t, which is illustrated or defined graphically. In this particular case, we can see that this signal x of t is going to repeat with every fundamental period, with every period t naught equal to 4. Let's take a look at a couple of other examples. So which of the following two signals are periodic? So x of t is cosine of t plus sine 4t, and y of t is cosine of t times sine 4 of t. So let's take a look at the first function. We have x of t is equal to cosine of t plus sine 4t. So in this case, we can see that the two independent signals, or the two individual signals that constitute our overall signal, are themselves periodic. So in this case, we want to know whether the sum of two periodic signals is also periodic. Well, we should identify that cosine of t is periodic with period 2 pi. We can also identify that sine 4t is going to be periodic with period pi over 2. So what we have to do is to take a look at whether there's a lowest common multiple of 2 pi and pi over 2, and if so, this will form the period of our overall signal. In this case, we can see that the lowest common multiple between 2 pi and pi over 2 is going to be 2 pi. So that means our overall signal is going to be periodic with period 2 pi. So in this particular case, the sum of two periodic signals is itself a periodic signal. Let's take a look at the second signal. Y of t is equal to sine 4t times cosine of t. So in this case, we should identify again the two individual signals that constitute our overall signal are themselves periodic, and we'd like to know whether the product of these signals is periodic. So we can rewrite sine 4t cosine of t using trigonometric identities. This is simply going to be a half times sine of 4t plus t plus sine of 4t minus t, or effectively a half sine of 5t plus a half sine of 3t. So now we actually have the sum of two periodic signals. So this looks very much like the previous example. We should be able to identify that the sine of 5t is a periodic function. And in this case, the period is 2 pi over 5. The second signal, sine of 3t, we can identify as also being periodic with period 2 pi over 3. So now we have to take a look and see, is there a lowest common multiple between 2 pi over 5 and 2 pi over 3? And if so, this will be the period of our signal y of t. Indeed, the lowest common multiple between 2 pi over 5 and 2 pi over 3 is 2 pi. So our signal y of t is also going to be periodic with period 2 pi. So in this particular example, the product of two periodic functions or two periodic signals is also a periodic signal. If you have any questions, please send me an email.